For a split second, it appeared that time travel was possible. An international team of physicists looking for loopholes in the laws of physics successfully used a quantum computer to reverse the age of a particle 1/1,000,000th of a second.
To be clear, this particle was not sent back in time, but researchers were able to simulate the process. So, is time travel possible? Researchers say that remains to be seen, but we want answers today. So we brought in an expert, astrophysicist for the National Science Foundation, Dr. Joe Pesce, who can share some knowledge with us on this front. He's the program director at the NSF Directorate for Mathematical and Physical Sciences Division of Astronomical Sciences, and we are very glad to welcome you back to the show, sir.
Thank you very much. It's very nice to be here.
Okay, so what were they able to do, and what were they not able to do?
So let me caveat this. Last time you had me, we talked about large, strange things,
yes.
And that large, strange thing was in my research area. And
yes.
Now we're talking about very small, strange things, and
strange things are very different than large, strange things.
Very, very different, and the world, the universe operates very differently. So
yes.
It's a very complicated system, and hopefully I can help translate that for you and your viewers.
I have confidence in you.
So this article that you mentioned, quantum mechanics underpins everything in the universe, and it's very interesting. It's weird. It's strange. It's mysterious.
It's way different than how the world appears
yes.
to work at these teeny,
yes.
tiny microscopic levels.
That's right. So the world around us, the macroscopic world, the classical world, we can say, is intuitive, right? We sit underneath an apple tree, and the apple falls on our head, and we understand that that's gravity at work. On the quantum level, the microscopic level, the atomic level, the universe operates in a way of probabilities, and it's difficult for humans to understand probabilities. That's part of the issue, and it's very counterintuitive.
Right.
And so but it's very attractive. It's strange and neat. And headline writers are enthusiastic as everybody else. And so these headlines come out and say that time travel occurred. Well, time travel did not occur. The article, in fact, was about quantum computing, which is maybe even a more interesting topic. So let's look at time travel. I think time travel is highly unlikely, and one of the reasons is from the quantum perspective. So you have a pool table with billiard balls, and
this is a quantum entanglement
yes.
image, which we can talk about in a moment.
Yes, indeed. So you have your billiard balls. You strike one against the other, and you see it move off on the billiard table. You record that and play the video back, and things go backwards. And you think, well, okay, that's time travel. If I'm going backwards in time, I can do the same thing. The problem is that you need to go backwards in time. You need to have the billiard ball move back exactly in the same way and end up at exactly the same spot that it started at. Right? So that's difficult in the macroscopic world. Maybe not impossible, but it's difficult. At the atomic level, the problem is that quantum mechanics tells us that at the atomic level, probability and superposition exist. What does that mean? So you have states of physical states, position and velocity, say, of a particle. And there's a probability of the position, and there's a probability of the velocity. And the strangeness of this is that, in the macroscopic world, we can measure both of these with the billiard balls. At the quantum level, we can't. We can only measure one, not both of them. So if we measure position to high accuracy, we don't know what the velocity is. Vice versa, if we measure the velocity to high accuracy, we don't know what the position is. And in order to go backwards in time, you need to know both. So let's say that we shrink our billiard ball down to an atom size. Well, in order to make it go backwards, we need to know where to strike the ball, how hard to strike it, and where it is. But I can only measure the position.
Can only know one of those
I can't
things.
tell how hard to hit it, or I know how hard to hit it, but I don't know where it is. Meaning that there's no way that I can make that particle go back to arrive at exactly the point that it was before, which is what's required here.
Interesting.
Yes.
So you mentioned that quantum entanglement was involved. Is that with the quantum computing?
So the subject of the article was quantum computing, in fact, and they were doing an experiment, in fact, a simulation. And a lot of work in quantum computing is, in fact, simulation. And that's one of the aspects of quantum computing. So it's an interesting result on its own. Quantum computing is quite an interesting field. It's a fundamental field of research at the moment. The National Science Foundation, among others, has been funding quantum computing for the last 30 years.
And what is the hope of what you can do with quantum computing?
So quantum computing, the issue with quantum computing is that there's more that can be done, because in classical computing you have a bit. We've all heard of bits. And bits can be in two states, one of two states, 0 or 1.
Right.
In quantum computing, it's not a bit, it's called a qubit. And a qubit can have a value of 0 or 1 or anything in between. So you have a huge increase in the amount of processing power, the ability to do computer operations.
So one of the classical theories, at least from lay people, around how time travel could actually work involves black holes, which is one of your specialties.
Yes.
Is that just totally outlandish, or is that still in the realm of possibility?
Well, so from a time travel perspective, of course, we don't know what happens when you fall into the black hole, right? So, does that shunt you off to somewhere else, like a wormhole, for example?
Right.
Which there's no evidence for wormholes. So the answer to that is we don't know.
What about relative time travel? I think that's in sci-fi. That's what everybody talks about, right? Which is speeding up relative to the current time here, and then when they would come back, it would be 30 years later, but it'd only be 2 years for them. Is that still technically possible?
Well, that's certainly. Well, it's a huge technical challenge, but certainly as you travel closer to the speed of light, for example, time does slow down, and so yes, there is. Now that's not time travel. It's just that time has passed more slowly for the individual traveling near the speed of light, or some fraction of the speed of light. So yes, that's certainly the case, but it's not time travel in the science fiction sense.
Not time travel in the technical sense, but it's probably as close as we would ever be able to get with immense technical leaps.
Don't kill my dream, Sagar.
This is my dream. This is cooler.
So I'm a Star Trek fan, of course, and on the original series, they use a gravitational assist by going near the sun and speeding up and then going back in time. But that's almost exactly analogous to the situation that I described with the billiard ball shrunk to the atom. So you have the Starship Enterprise, and not only do you have one atom now, but you have trillions of them in the starship that you need to move back to precisely the positions that they were previously, and so that's highly unlikely.
That would be hard.
Yes, indeed.
Dr. Joe, thank you. Great to have you back. We really appreciate it.
Yes, I appreciate it.
I enjoyed being here. Thank you.
Next on Rising, as more states impose more abortion restrictions, a surprising individual signals that the actions may be way too extreme.
And the latest Democratic 2020 candidate joins the other mayors in the presidential primary. Nancy Pelosi and AG Bill Barr play verbal chicken over the Mueller investigation fallout. So Team Rising is here to share their takes next.